Bismillahirrahmanirrahim and Assalamu alaikum. Today we are going to start the predicates and quantifiers. As we have studied in the last lecture the basic definitions of predicates, quantifiers, we have studied also the existential and universal quantifiers. We have also studied the universal conditional statements, equivalence form, implicit quantification and the negations. Today we will continue the same topics but in some advanced level. So predicates and quantified statements too. Today we are going to study the statements and propositions which contains both quantifiers, existential and universal, and then we shall study also the nested quantifiers and the relation between them. We shall also study the universal modus ponens and modus tollens, and the converse and inverse errors of modus ponens and modus tollens. So let's see the statements which involve both quantifiers, existential and universal. For example, we are given the first example: for all positive number x there is a positive number y such that y is less than x. How we can write or say this statement informally? Given any number, for all numbers x means given any number, there exists a positive number y such that y is less than x. So we can say it in simple or informal language: given any positive number, there is another positive number that is smaller than the given number. So we can say this statement informally as another example in which there exists or existential quantifier becomes first and the universal quantifier at the second. So in this statement there is a positive number x such that for all positive numbers y is less than x. This is basically the reverse of the first statement, and we can say in informal language as there is a positive number with the property that all positive numbers are smaller than this number. Certainly there are many other ways we can say the given statements informally. Now if we see the informal statements, then how can we use the multiple quantifiers there exist and or existential quantifier and universal quantifiers at the same time? We consider these examples in which we shall write the simple English language statement or informal statements into logical statements using one or more quantifiers. For example, the first statement is, for example, everybody loves somebody. Now for everybody, for every, we will use obviously the universal quantifier which is for all, and for somebody we shall use the existential quantifier there exist. So such type of statements involve both quantifiers, universal and existential. So how to translate this proposition or statement into the logical statement? For example, everybody, how can we translate it? We say x is the everybody. For example, x are the people, and we write here for all people x. What does it mean? Everybody. there exists a person Y, there exists a person Y. Now there exists means somebody, so such that X loves Y. So how can we translate it? Every people, for every people there exists some person such that X loves Y. So what does it mean? Every X loves some Y. So we have translated the informal statement into a formal logical expression. Similarly, if we reverse this statement, somebody loves everybody, then the existential quantifier will come first. For example, there exists a person X. Now we have somebody here such that for all people Y. Now here everybody comes at the last so the universal quantifier will come here for all people Y. X loves Y. So we have translated the second statement into the logical statements. Another example, any even integers equal twice some other integer. Now here we have any means, here we can take it as every. Any means whatever the integer is, we can take it any even integer. Now here we have even integer equals twice some other integer. So now how to translate it into the logical form? We take m as an integer and we say any for all even integers m. So we have translated the first part of the statement, any even integers, here for all even integers m. So equals twice some other integer. Here we have some, here we have some. Some means there exists at least one, you can say it. So there exist integers n such that, here you can write such that n is equal to 2m. So because every even integer can be written as the multiple of 2 of some integer. So here I think there is a mistake here. I should write here m is equal to 2n, because m we have suppose here m as an even integer. So this is even integer which can be written in the form of multiple of 2. So any even integer equals twice some other integer. So we can translate it for all even integers m, there exists some integer. Now n is not necessarily even. N here may be any integer. For example, if we take 4 as m, then how can we write 4? 4 is equal to 2 into what is the multiple here? 2. So what is n here? N is this and m is 4. So any even integer can be written in the form of the multiple of 2. Here this integer I told you is not necessarily even. So if we take 6 as m, then we can write it as 2 into 3. So here you can see 3 is not even, 3 is odd. So this statement is only for the even integers. So we can translate this informal statement into a formal statement. Another example, there is a program that gives the correct answer to every question that is posed to it. It means there is a computer program, if we put any question in this program, it will give the correct answer. So what is there exist here? So the first statement here we can see that there is a program. So there is a program means there exists at least one program that gives the correct answer to every question. Now every is coming here. So in this statement we can observe that we must use the existential and universal quantifiers, and we say the program P. Now P is any program, and we use here the existential quantifier. There exists a program P such that for all questions it gives correct answer. So there is no need to use this because it is obvious. Whatever the question we pose to the program, it will give you the correct answer. So sometimes there are some unnecessary explanation in the statements which we can omit or we can leave. So there is a program means we'll use the existential quantifier that gives the correct answer to every question, and every question we will use the universal quantifier. So we can easily translate this statement into the logical statement using multiple quantifiers. Next we shall see the negation of the statements. In the last lecture we have seen the negations which involves only the one quantifier, there exists, or the universal quantifier, and we have seen that we convert the existential quantifier into universal quantifier in the negation. Here we have statements which involve two quantifiers, for all, or existential and universal quantifier. To take the negation of such statements, for example, we are given the statement this: for all x there exists y such that p of x y is true. Then how we shall negate this statement? As in the previous lecture, the universal quantifier will be converted to existential quantifier, and existential quantifier will be converted to universal quantifier. And then we'll take the negation of the predicate. We take the negation of this predicate here, not P, as I've told you that we can denote negation this, or we can denote it by this sign which is called tilde. So how to take the negation of the statements which involve multiple quantifiers? So we can take similarly, if we have statements of this type, there exists x such that for all y q of xy we have some other predicate. So again the existential quantifier will be converted to universal, and universal will be converted to existential here, and we take the negation of this predicate here. As an example, we consider here in part A we have for all integers n there is an integer k such that n is equal to 2k. In this example we have translated in the earlier slides that every integer every integer can be written as the multiple of 2. Here we must have how to basically here negate this statement. For all integers n, as I have told you, for all will be converted to existential quantifier. This universal quantifier will be converted to existential quantifier, and existential quantifier will be converted to the universal quantifier. So for all integers n, this will be converted to there exists an integer n, and there exists an integer k. For all integers k, this will be converted to this statement, and here we have n is equal to 2k. What will be the negation of n is equal to 2k? We say that n is not equal to 2k. What does it mean? That there exists some integer that is not even. So this is true, there are integers which are not even. So another example of this, in which we have used the existential quantifier first and then the universal quantifier, and existential quantifier here will be converted to the universal quantifier, and universal quantifier will be converted to existential quantifier. So here there exists a person x, it will be converted to for all people x, and for all people y will be converted to there exists a person y, such that here we have x loves y, and what will be the negation of x loves y? X doesn't love y. So, or we can say that nobody loves everybody. Here we have for all people there exists a person y, such that x doesn't love y. Means x is here everybody and y is somebody. So everybody doesn't love somebody. So, or we can say that nobody loves everybody. So this is how we can negate the statements involving multiple quantifiers. The next, we shall see what is the nested quantification. In fact, in nested quantification we have statements of such type. For all x there exists y, such that x plus y is equal to 0. In fact, two quantifiers are nested if one is within the scope of the other. Means this is somewhat in the same situation, but we say it differently, such as for all x there exists y, such that this is same thing as for all x q of x, where q of x is there exists y p of xy. Means y here is in the scope of x. So where p of xy is x plus y is equal to 0. Nested quantifiers commonly occur in mathematics and at many places in computer science. To understand well the nested quantification, we consider some examples, but I repeat here. Basically, in nested quantification, one variable is in the scope of the other variable. So let's take some examples. For example, here we translate this statement into the informal language or into simple English language. If we have for all x, for all y, x, here we have brackets, x greater than 0, and we have and here y less than 0. This implies product of x, y is less than 0. This is basically if you have one positive number and one negative number, then the product of these two numbers will obviously be negative. For example, if we have 2 into minus 3, then the product is obviously minus 6. So one is positive and one is the other is negative. So the product of a positive and negative number is always negative. This is what we have said in this statement. With the domain for both variables are real numbers. So how can we translate this statement? The product of a positive real number and negative real number is always a negative real number. So here y, you can say y is in the scope of x. First we take x, any real number, and then y we take within the scope of x. Means y we take a negative number, then we take the product so the result will be a negative number. So another example of this, write the following statements in English using the predicate S of xy. X shops in Y. So X here represents some people, any person, and Y represents stores. So people shops in stores. Here we can, this statement represents every people, every person. You can say that every person, any person shops in Y means. So there are two statements here which we have to translate. Here you can say that here you can see that for all Y, this is the example of nested quantification, that for all Y, S of, here he has written John Y. So John here is basically in the scope of Y. So we can say this in nested quantification. So we have to translate this statement for all Y, S of John Y. John is basically here some person. So for all Y means in every store John shops. So how can we translate it into simple? John shops in every store. Every stores, because we have for all Y. For all Y means every store, but John is single here. So John shops in every store. I mean, John जो है shopping करता है तमाम store से. Another example is there exists X, there exists some people, there exists some person. For all Y, every store, S of xy. What does it mean? There is a person. Here we have there exists a person, or there is a person who shops in every store. Because S of xy is basically X shop in Y. X in this statement is there exists, and Y in this statement is for all. So here we can say that there is some person who shops in every store. So such type of quantification is said to be nested quantification. Next we see the table in which we shall see the statements which involve multiple quantifiers. For example, in this table we shall see the multiple quantified statements, or the statements which involve multiple quantifiers, when these statements are true and when these statements could be false. The first statement is for all X, for all Y, P of xy. Basically this is equivalent to this. We can say for all Y, for all X, P of xy. So when this statement will be true, P of xy is true for every pair xy. So here we have two universal quantifiers for all. For X we can say every X, and for every Y, P of xy is true. Now when this statement will be false, we can say that what is now first, what is the negation of universal quantifier? Negation of universal quantifier is basically negation of universal quantifier which is applied to some proposition is basically equivalent to the existential of the negation of that variable, as we have seen earlier. Or simply you can say the negation of universal quantifier is existential quantifier. Now here we have two universal quantifiers. Now P of x is true for every X and for every Y. You can say when it will be false, it will be false when there exists some pair xy for which P of xy is false. So only one pair X of X and Y is enough, is sufficient to prove this statement to be false. Now here we have to be very careful to decide when this statement will be true and when this statement will be false. Here we have universal quantifier for x and existential quantifier for y. So here for every x there exists y for which p of x is true. Now in the negation, for all the universal quantifier will be converted to there exist and existential quantifier will be converted to for all. So when this statement will be false, when there exists some x such that p of xy is false for every y. So we have inverted the quantifiers. For all means universal quantifier. Here we have for every x, here we have there is some x or there is an x, and here we have there is a y, here we have for every y. So in the true false of these statements we take the negation of these statements. Basically you know that the negation of true is false. So when this statement will be false, there is some x such that p of x is false for every y. Another statement is, now in this we have inverted the universal and existential quantifier. There is some x such that for every y p of x is true. So there is some x for which p of x is true for every y. Now here the existential quantifier is converted to universal and the universal quantifier is converted to existential. So for every x there is a y for which p of xy is false. Similarly we can see how these statements could be true and false. So here we have there exists x, there exists y, means there is at least one x and there is at least one y for which p of xy is true. The converse of basically the negation of this statement, or this statement could be false when p of x is false for every x and y, because here we have existential quantifier for both variables x and y. So the negation will be the universal quantifier for both variables. So when this is false when p of x is false for every pair of x, y. So I hope you understand how to interpret the truth and false, or the truth values of the statements involving multiple quantifiers. Let's see an example of this situation. Write the following statement in English using predicates. C of x is basically x is a computer science major and t of xy is x is taking y. The domain x basically obviously are the students and y represents the courses. Y is any course, you can say in the BS or in the computer science department. Now we have to translate this statement and we shall see when the statement is true and when it will be false. Here we have universal quantifier, here we have existential quantifier, and here we have negation of c of x, negation of c of x. C of x is this, then what will be the negation of this c of x? X is not a computer science major, this will be the negation of c of x. And t of xy, what is t of xy? X is taking y, x is student, means student is taking y, y is some course. So this statement says that every course y, means here we have universal quantifier, means for every course y there exists some student x such that x is not a computer science major and x is taking y. So informally we can say this statement in every course, because we have universal quantifier with the y. So in every course there is a student who is not a computer science major. So we can translate this statement, and when this statement will be false or when this statement will be true. If in every course there is a student who is not computer science major, mean there are some engineering or some other discipline students which are taking this course. So when will be this statement false? So for all will be converted to there exist, and there exist or existential statement will be converted to for all. We can say that there exists some course in which every student is not a computer science major. So we can negate this whole statement to get the values for which this statement will be false. So we can say that there exists some course in which every student, because here we have there exist, so there exist will be converted to for all or universal quantifier. So there exists some course in which every student is a computer science major, because here we have to take the negation of this also. Who is not a computer science major, the negation of this is a computer science major, you can say. Now what is the relation between the existential, universal, disjunction and conjunction operators? So if q of x is a predicate and the domain d of x is the finite set which contains finite many values from x1 to xn, then the statements for all x belongs to d and q of x1, there is a conjunction operator between them, q of x2 conjunction operator, and so on, q of xn. These two statements are logically equivalent. Here, as I have told you earlier, that by using the method of exhaustion we have proved some example. So this is the same as if we, what does it mean? For all x belongs to d, d is basically the domain, or you can say the universe of x. Q of x is true. This is equivalent to q of x1 is true and q of x2 is true, and so on, q of xn is true. So these are basically the two equivalent statements which shows the relation between the universal and conjunction operator. For example, we say that if we say that d is basically 1, 2, 3, for example, this is the domain, and we can say that q of x to be x square is greater than or equal to 1. Now we can say for all x belongs to d, q of x is true, because if we put 1 here in x, 1 square is greater than or equal to 1, this is true. 2 square is greater than or equal to 1, this is also true. 3 square is greater than or equal to 1, this is also true. Or we can say that q of 1 and q of 2 and q of 3, this is true. So saying this is equivalent to saying this, because we have universal quantifier here. q of 1 is true, means 1 square is greater than or equal to 1, and 2 square is greater than or equal to 1, and 3 square is greater than or equal to 1. So this is true, this is true, this is true. There is a conjunction operator, and you know that conjunction operator, if we have p and q, two propositions, then this is true when both p and q are true. So these two statements, in which in the first statement we have used the universal quantifier, and the second statement we have conjunctional operator. So these two statements are logically equivalent. So here we can say that let q of x be x and x is equal to x, and suppose d is 0 1, then for all x belongs to d, q of x can be written as, for all binary digits, x, x and x is equal to x. This is equivalent to saying 0 and 0 is equal to 0, and there we have used the conjunction 1 and 1 is equal to 1. Means here you can say that 0 and 0, and basically this is 0, and the other is 1 and 1 is 1. So similarly, there's a relation between existential and the disjunction operator, or the statement there exists x belongs to d, q of x, and q of x1 or q of x2 or so on, q of x n. These two statements are basically logically equivalent because their truth values will be same. Here again the d is the finite set which is the domain of x. Again we can consider another example, a simple example. If we have d is equal to 1 2 3, the same example, but we change here the predicate. Now we can say that x square is equal to 1. Now if there exists some x such that x belongs to d, such that q of x is true. Now this statement is true because for 1 this statement is true, but for 2 and for 3 this statement is false. So there exists some x belongs to d such that q of x is true. So we can write this statement equivalently as q of 1 or q of 2 or q of 3. Now if one of, what is q of 1? This is basically 1 square is equal to 1, or 2 square is equal to 2, or 3 square is equal to 3. Oh sorry, 1. This is 2 square is equal to 1 and 3 square is equal to 1. So now only this portion is true and the other two portions this are false. Even then, you know, the disjunction operator is between these two propositions or statements. Now if one proposition is true, then the disjunction of two or more proposition will be true. So these two statements, this and this, are logically equivalent. Next we see the rules of instantiation. What is this rule? This rule says if some property is true of everything in a domain, then it is true of any particular thing in the domain. For example, if I say that all students in the discrete mathematics class are older than 20 years, then if we take some particular student, for example John, then John will obviously he will be older than 20 years. So this is basically such type of rule in which we say that if a property is true for everything, then that property will be true for a particular thing. For example, if we take this example in which all human beings are mortal, we can say that हर इंसान को मरना है, and then Socrates is a human being, Socrates is a human being. अब Socrates जो है वो अगर इंसान है तो उसको भी लाजमी मरना है. So this is basically rule, we say it the rule of instantiation. So if we take another example, suppose you are doing a problem that requires you to simplify this, where r is a particular real number and k is a particular integer. For basic algebra we know that these two rules are generic, or these two rules hold for every real number and for every two integers m and n. Here we have multiplication, means we can say it has xm dot or into x n. This is basically x equal to m plus n. So again, the second rule says us that x power 1, any real number power 1, is same as that real number. So we proceed as follows: r k plus 1 into r. Now here r can be written as r power 1 using this 2, using 2. Now we can use 1 here. We can add the powers of r. K plus 1 is k plus 2. So we have used these universal laws or rules of mathematics, which are true for any real number and any two integers m and n, and this is also true for any real number. So we have used here in a particular form. Here these rules are in general form. So in mathematics we use the general results as in the situation we need them particularly. Next we start the universal modus ponens. Now what is the formal and informal forms of universal modus ponens? Here, for all x, p of x implies q of x. Basically this is the first statement of universal modus ponens. Here now we have for all x, means in usual modus ponens, in simple modus ponens, as we have studied in previous lecture, we have seen that we don't have this form, universal quantifier. As you know that we had this form, p implies q, p therefore q. So this is basically the simple form of modus ponens. Now the in the universal modus ponens we have introduced the universal quantifier for all x. Now what does it mean? It means that for all x, if p of x is true, then q of x is true. Means here for all x, if p of x is true, then q of x will be true. And the second statement is p of a, for some particular value of a, p of a is true, then the conclusion is that q of a will also be true. In the informal version I have explained you that if every x, you can say that if x makes p of x true for every x, then x makes q of x true. Here we have chosen a particular value of x. We can say it, if x is equal to a, then p of a is true. For a particular value of x, if p of x is true, then we can say that for that particular value q of x will also be true. So this is the universal modus ponens, in which we have introduced the universal quantifier. We consider an example here. If a number is even, now if a number is even, now then its scale is even. Now this statement is true for all even numbers. So we can introduce here a universal quantifier to translate it for all x, e of x. E of x, what is e of x? X is even, and s of x is square of x is even. Now we have introduced here the universal quantifier for all x, and we have translated the first statement into this. This is basically equivalent to saying that if a number is even, or you can say that if any number is even, then its square will also be even. So now here we take k. K is any particular number that is even. For example, we can take x is equal to 6. Now e of 6, here you can say e of 6 is true, then s of 6 if x is 6, then e of 6 is true. If e of 6 is true, e of 6 means 6 is even, then s of k, s of 6 will also be, means square of 6 will also be even. So this is basically the example of universal modus ponens. I repeat here, if a property is true for, here the first property is true for every x, if we take some particular value of x here and saying that e of that value is true, then s of that value must be true. Next we take the universal modus tollens. Now, like the usual modus tollens which we have studied in the previous lecture, in the universal modus tollens we introduce the universal quantifier for all x. The first statement is same as universal modus tollens. Here we take, if q of x is false, you can say not q of a is true, then not p of a will also be true for any particular value of x. Informally you can say that if for any x which makes p of x true, then q of x is also true for any x or for all x. And as in the usual modus tollens, a, we take here the particular value of x is equal to a. If a doesn't make q of x true, then obviously a doesn't make p of x true. For example, here if we say that all human beings are mortal and zu is human being, if we take here zu is a human being, then therefore zu is mortal. Now how to translate it, this example, as a universal modus tollens? If we take h of x, x is a human being, m of x as x is a mortal, and z stands for Zeus, then the argument becomes for all x, if h of x then m of x. Here we see not m of z implies, or therefore not h of z. What does it mean? That if all human beings are mortal, what does this statement means? That Zeus are not human being or not mortal, then Zeus is not a human being, because here we have m of z. M of z means x is mortal. No, not m of x. What does it mean? It means x is not mortal. So here we take some particular value of x as z and we write here not m of z. It means that z means Zeus is not mortal. So by the universal modus tollens we can conclude that Zeus is not a human being. Now what is the converse error in the quantified form? What is the converse, and in the next we shall see what is the inverse error, as we have seen in the previous lecture. Now here the forms involve the universal and existential quantifiers. These are basically the quantified forms. Now if we say that for all x, if p of x then q of x, and q of a for a particular a, and we conclude p of a. So what is the error in this statement? Here if q of a is true and p of a is false, even then this statement will be true. As you know that the conditional statement p implies q is true when p is false and q is true. So if we take here q of a to be true, p of a to be false, then p of x implies q of x for all x. This statement will become false. So this is basically the same error as we have discussed in the converse error of the usual modus ponens. We take an example. All healthy people eat an apple a day. So we break up it in, we say m of x, x is a healthy people, h of x, x eat an apple a day. So we particularize here Alan eats an apple a day. So now here we have used q of a. This is basically the q of, sorry, h of a. H of a where a is Alan. So we conclude here Alan is a healthy person. So what is the error in this argument? The error is that we cannot take here the conclusion, this. In the usual modus ponens we know that p implies q. Here we must have p and we conclude that therefore q. We cannot write here q. We cannot write here p implies q and q therefore p. So there is a difference between these two argument forms, as in this, in the correct form of modus ponens we have p here and we conclude q. If we write q here and conclude therefore p, then this form is basically the invalid argument. As if we take q to be true and the whole statement is true, then p may be false. Even then this conditional statement is true. This is true here and q is true, then q must be false, then p must be false here. So this is the error in the universal modus ponens, which is called the converse error. Similarly, we can see the inverse error. Inverse error for all x, if p of x then q of x is true, and we say that not p of a is true, then not q of a is also true. So this is the same error which we have studied in the universal modus tollens, in the usual modus tollens. The same example we consider here, but we change the person here. All healthy people eat an apple a day. Smith is not a healthy person. Smith doesn't eat an apple a day. So if we translate this argument into the logical form, h of x is healthy person, m of x eat an apple a day, and s stands for Smith. Then for all x, if h of x then m of x, and we say here not h of x, and we conclude not m of s. Now if not h of x is true, then this will be false, and this statement is in general true, and there is possibility that if this is true, even then this conditional statement is true, then we cannot m of s is true, because here there is a possibility that m of x could be false. If m of x is false, even then as a whole this conditional statement will be true. So we cannot conclude here whether not m of s is true or false. So there is again an error in this argument form, which is called the inverse error, and such type of errors occur usually in the modus tollens forms or tollens arguments. So for today we stop here, and in the next lecture we shall start some a new topic, which is a number theory. So in today's lecture we have discussed the statements which contains multiple quantifiers. We have studied the nested quantification and the relation between the universal, existential, conjunctional or disjunctional operators. We have also studied the universal modus ponens and universal modus tollens, and studies the errors in these valid argument forms. Allah Hafiz.